Welcome back, Chemistry Theory. This is EQ 3.5, the pH scale. So we'll calculate the pH of a solution given the concentration of hydronium or hydroxide and multiple other type questions. The molar concentration of H plus in an aqueous solution is usually very, very small. So we're talking about small amounts of H ions being present in acidic solutions or OH in basic solutions. For convenience, we therefore usually express H plus in terms of pH. And pH, if you recall, represents potency of H plus ions. So that's where the pH comes from. And it's a negative logarithm in base 10 of H plus, like that. Before we look at that, though, we should take a look at logarithmic scales, though. If you could maybe turn to the back sheet here in this section, we have a bunch of pH values, etc., but we also have some room on the bottom where we can copy out some stuff or discuss a few things. So first of all, if we look at a XY coordinate system, and let's say we have a graph that looks like this. You of course know that's an exponential graph. Okay, maybe we could say it's y equals 10 to the x. So if x is 1, y is 10. If x is 2, y is 100, etc. So it would increase substantially like that. Now, what you would have taken in an earlier math class is if we have a line that's y equals x, we could look at what the inverse of that would be. So the inverse graph would be something like this, reflected around y equals x. To get the equation of that, we interchange x and y. And of course, with the equations, we represent them in terms of y equals something. So in order to bring that y down from the exponent, one of the things you would have done is take the log of each side. Oops, log 10y. And of course, what happens there is one of the rules with logarithms is that what was an exponent will now be a variable out in front. And if we use log here, log is taken to be base 10. So the result of this portion of the equation would be 10 to what exponent is 10? Well, we know that as 1. So log x is equal to y, or y is equal to log x. So that is the formula of that graph right there. Now, if we're looking at having y and x actually equal to something in real life, the y-axis, if we represent as pH, and the x-axis as h. Now, before I get into that, the relationship here with logarithms and H plus concentrations, etc. This is y equals log x. If we reflect that around the x-axis, so it's like we take it and flip it over top, or like this, I guess we could say flip it that way. This is the one that is going to be beneficial for what we're looking at here. This exhibits the pattern of pH when we're looking at H plus ions. So y is represented by pH, and x is represented by, or x is represented by log, and that is what we have there for a relationship. So as concentration of H plus increases, the pH decreases. And we can look at various values here involving pH and concentration of H. If we look over here, if we take, let's say, the log of 1, 10 to what exponent is 1? 0. Or if we could take a look at negative log of 0.1. If I take that over to the opposite side, 10 to the 2 is, or sorry, 10 to the 1 would equal that, etc. Negative log of 0.01. 10 to what negative gives me that? 2. Okay, so we can see here as the concentration of H increases, going from here to here, the pH, if H plus increases, the pH decreases. So this is the relationship that we're looking there. So for every factor of 10, we'll see on this part here, we'll leave it to the end of the video, that the pH changes by 1. Now you may be familiar with this with the Richter scale. It's a logarithmic scale. For an earthquake of 2 versus an earthquake of 3, the earthquake of 3 is 10 times more severe than an earthquake that's 1 unit below that. But we'll come back to that. So if we look over here, so that's the relationship there between pH and H plus ions, because these tend to be very small. Like for example, 1 times 10 to the minus 8, that's a really, really small number. So as human beings, we like to use numbers in between 1 and 10. So it kind of converts that into a number between 1 and 10. So this equation can be used to calculate the pH of a neutral solution. So if we look at, remember last section, for a neutral solution, we have H equaling OH, which is 1 times 10 to the minus 7. So if we were to use that over here and figure out, well, what is the pH of a neutral solution? So negative log of 1.0 times 10 to the minus 7. If you plug that in your calculator, of course, if you're familiar with logarithms, there's a few tricks we can use here, and we'd see that it actually equals that exponent up there. Okay, I'll just write it to 2 decimal places. So the pH of a neutral solution is 7. And you may have encountered that earlier on in other classes. If the solution in question is made more acidic so that H increases, the smaller the pH becomes because of that relationship, that logarithmic graph that we just looked at. Over here, if we look at as H increases, the resulting pH decreases. So let's look at it. If I had 1 times 10 to the minus 3, this is a way bigger number than 1 times 10 to the minus 7. So pH equals negative log of H plus. So negative log of 1.0 times 10 to the minus 3. And by how that number is set up, it's equal to 3. So it's a lower number on a pH scale means more acidic. The pH of a basic solution can also be calculated, one in which I have OH bigger than 1 times 10 to the minus 7, so that neutrality point. If I have an OH concentration bigger than that, we could figure out what the pH is, etc. So if I had OH equaling 2.0 times 10 to the minus 3, determine the H and then the pH of that solution. So if I look over here, so we had that one relationship here from the other video. Concentration H times OH must equal 1.0 times 10 to the minus 14. So if I know what OH is, I can easily figure out what H is. So divided by 2 times 10 to the minus 3 on each side. And H equals 5.0 times 10 to the minus 12 molar. Now that I know what H is, I can figure out the pH of that solution. So the negative log of 5.0 times 10 to the minus 12. So take the negative log of that number, and we would see that the pH 11.3. So that's higher on the pH scale. A higher number on a pH scale, higher than 7, means it's basic. If it's less than 7 on the pH scale, it's acidic, as we see from this next chart. So if we take a look over here, a neutral solution, H and OH are each 1 times 10 to the minus 7, and the pH is 7. If I have an acidic solution, my H is going to be bigger than that number. My concentration of OH is less than that number, therefore the pH is going to be less than 7. If I have a basic solution, so that means my H plus has a concentration less than it would be if it was neutral, and OH is bigger than if it was neutral, that gives me a larger pH than 7. Let's take a look at another example. Let's look at pH. What if H is 5 times 10 to the minus 6? So negative log of 5.6 times 10 to the minus 6. Now if we take a look here, is this number bigger or smaller than the neutral solution? 10 to the negative 6 means that this decimal is only 6 places to the left, whereas there it's 7. So this should be a bigger number. So we would expect it to be acidic, which means pH is going to be less than 7, because that is true for acidic solutions. So let's see what we get here. If you plug it in your calculator, yes, we get 5.3. 5.3 is the result. All right, well, I'll stop the video there. Then part 2, we'll continue on with the next question.